continue. As I've explained in the previous videos in this series, before you can understand corrosion, you must understand what electricity is and how we measure it. Electricity is energy that can be measured using instruments. Gibbs free energy is a scientific theory that proves that free energy immediately fills a void. This means that there is no such thing as zero energy, and therefore there can be no such thing as negative energy. You cannot say take something from nothing. Confusion arises from the fact that for every force there is an equal and opposite force. This does not mean there is a negative force. It means there is another force going in the opposite direction. If there's no such thing as zero energy, why is there zero on all of our meters? This is because we are making comparative measurements. And if there is exact equality between the two inputs of the meter, zero will appear on the display. We can test this by simply joining the leads together as a continuous metal conductor between the two inputs. The meter will read 0. So I will take these two leads and I will connect them together and switch the meter on, and we have the reading of 0 because there is no energy between the 2 ports of the meter. If we put a dry cell battery between the 2 ports, then we will see the potential energy of a corrosion reaction. This is sometimes called the electromotive force and is measured by comparing it with another electromotive force or potential. The meter displays the difference between the potentials at the holes where we plug in the meter leads. Early corrosion engineers put a piece of copper in a saturated solution, in a saturated solution of copper sulfate, and put this on the ground in order to get a voltage measurement between the piece of copper and the metallic connection to the pipeline. They called the copper in a saturated solution of copper sulfate a half cell. They carried out tests and recommended that if you got a reading of negative 0.850 volts, that's 850 millivolts on the meter, the pipelines would not corrode. Switch this off for the moment. It seems that they related this to the diagrams produced by a scientist called Pourbaix and some equations worked out by guys called Nernst and Einstein. There's a lot of stuff written about this, so I will not repeat it here. However, pipelines continue to leak when the value of negative 850 volts was obtained. Attempts are still being made to justify this criterion. Some corrosion engineers tried to applying a shift of 0.3 volts, that's 300 millivolts, from what they described as the natural potential, but still pipelines leaked when they met this criterion. Others said that a shift of 100 millivolts would do the trick if it was taken immediately the cathodic protection system had been switched off. It seems that I am one of the very few people who recognise that the basic error is in the measuring procedure itself. I looked at the circuit diagram and asked the reason for the use of copper in the saturated solution of copper sulfate. I was told that copper in a saturated solution of copper sulfate has a known potential. This is not true. It varies with temperatures. Copper sulfate is produced industrially by treating copper metal with hot concentrated sulfuric acid. For laboratory use, copper sulfate is usually purchased. I bought this on the internet, no problem. The copper used in wire has to be pure, as this determines the conductivity. So we can strip some wire for our experiments. We can also buy copper rods, like this one. This is a metre of 1/4 inch copper rod. I bought it at a local hardware retailer. So, we can put the copper sulfate solution in any non-conductive container and use any material that is absorbent. This is a piece of wood. This is a non-conductive container. And we make the wood, soak the wood so that it is an electrolytic conductor. This bit of wood is sticking out of the top. I've put some blue tack to hold it in place. This is a piece of copper wire, and we now have a half cell that we can measure. I have used this arrangement in a whole series of experiments that you can study online. I am now connecting the red lead of the meter to the copper, and the black lead, which is the common, to the wood, which is soaked in the saturated solution of copper sulfate. The first experiment is to find out if the half cell is a stable reference potential by measuring the EMF of the reaction between the saturated solution and the copper. You can see that on this meter it is about 1.4, so that's 1.4 millivolts. There you go. It's not very steady. The meter is not very sensitive. I can now use another meter oops. I plug the voltage, the red one, to voltage, and the black lead into the common. I have put it on to 200 millivolts there, and I switch it on. This shows approximately 5.2 millivolts as the EMF between the copper and the connection to the wood, which is in the saturated solution of copper sulfate. If I then reverse the connections, we have a reversed reading, a negative reading on here. This says that it is negative 8.8. And this is very interesting because the other reading was positive and the other reading has changed. No, that was bad connection. 8.9, 8.8, 8.7. The interesting observation with this slightly more sensitive meter is that the voltage is dropping. So it's not constant. So we change them over again. And we see the negative reading building up, 8.8, and that is steady, negative 8.8 millivolts, 8.7, and I will change them again so that you can see that they are not constant. 8.8, and this will start to reduce. 8.7, 8.6, 8.5. This indicates that the corrosion reaction, or the cell reaction, it's not a half cell, it is a cell. The cell reaction in this electrode, which is a copper sulfate cell, which is called a half cell, and this is not of constant value. I am measuring between the copper sulfate solution and the copper itself. It is not a fixed potential, and it is not a constant potential. It cannot be used as zero in our measuring circuits.